This video is for lesson 14-3, perpendicular bisectors and angle bisectors of a triangle. Learning goals are to determine the points of concurrency of the perpendicular bisectors and of the angle bisectors for a triangle, and then use these points to solve problems. So this will be our last lesson about the activity involving that piece of land and the treasure and so on. Al, Jeff, and Cal found the treasure by locating the point of concurrency of the altitudes of a triangle called the orthocenter and the point of concurrency of the medians of a triangle called the centroid. With those values, they were able to get the combinations to the treasure chest locks. Cal tells Al and Jeff to learn about two more types of concurrent points called the circumcenter and the incenter before they design the nature preserve. Over here on the side in the green boxes, you see the definition of these. So the perpendicular bisectors of the sides of a triangle are concurrent. Their point of concurrency is called the circumcenter. So to find the circumcenter, we would find the perpendicular bisectors of the sides of the triangle. The incenter. The angle bisectors of the angles of the triangle are concurrent, and the point of concurrency is called the incenter. So to find an incenter of a triangle, we would need to find its angle bisectors. Okay, let's work with these today. Number 2, Al took an algebraic approach similar to the manner in which he found the orthocenter and centroid of the triangle. And he calculated the circumcenter to be at 18,6. Jeff decides to carefully sketch the perpendicular bisectors of each side of the triangle. And that's what we're asked to do here. So we want to draw the perpendicular bisectors of the sides of the triangle and label their point of concurrency Q. We're going to have to follow a technique that Al must have followed when he did algebra. So to find a perpendicular bisector, for example, of the bottom side of a triangle, we need to first bisect that side. We have to find the middle. And even by using algebra, Al would have had to do the same thing. So that is 36 units long. The midpoint would be at 18, which is right here. We want to draw a segment through this spot that's perpendicular to the side. Because this is horizontal, we want to draw vertical, like this, crossing that at a 90-degree box. Okay, next, let's find the perpendicular bisector of the left side of the triangle. Again, we have to bisect that side, so we must find the middle. So if you count over 1 up 2, over 1 up 2, you'll find that you can repeat that 6 times. So if we do it 3 times, that dot right there ends up being the midpoint of this side. Hopefully you recall that same technique from the other day when we drew from the angles to the midpoints of the sides. Now we want to draw a perpendicular bisector, so we want to draw a segment whose slope is the opposite reciprocal of the slope of this side. This has a slope of 2. The opposite reciprocal of 2 is -1/2. So down 1, right 2, down 1, right 2, down 1, right 2, and so on. So draw this segment in like this. Again, it crosses the side or touches the side at a 90-degree angle. Okay, there's one more side of the triangle to do. Again, we need to find the exact middle point of this. So I'm going to just count the diagonal units and then find what half of it is. And that would cross right there. There's the midpoint of that side. The slope of this is -1, so the opposite reciprocal of -1 is +1. And we can do a +1 slope to get the correct angle for drawing this line. Okay, notice that these 3 brown lines are the perpendicular bisectors of the sides of the triangle, that they are in fact concurrent, and we were told to call this point Q. And we have visually confirmed that point Q is at 18,6, which is the answer that Al got when he did algebra with equations. Does our drawing verify Al is correct? Yes. The circumcenter of a triangle has a special property. Use the distance formula to complete the following table. Let's find the distance from point Q to point A. So here's Q, the point we just found, and here's A, this vertex of the triangle. We're asked to find this distance using the distance formula. So we would do the square root of the difference of the x coordinates squared. It'd be like this, right? So 18 take away 0 squared plus the difference of the y coordinates squared. 6 take away 0 squared. When you simplify this out, it makes 6 square root of 10. Then find the distance from point Q to point C. So how far is it from this dot to that vertex? Again, use the distance formula to subtract the ordered pairs of those points, and you also get 6 square root of 10. Likewise, the distance from here to point G is 6 square root of 10. Does that suggest a special property? The distances suggest that the circumcenter is equidistant from the 3 vertices of a triangle. Write a convincing argument for this. So an argument might go something like this. Points on the perpendicular bisector of a segment are equidistant from the endpoints of that segment. And because point Q is on all 3 perpendicular bisectors, it must be equidistant from all 3 vertices. Problem 5, we're asked to draw the circumscribed circle on the grid on the previous page. A circumscribed circle is a circle that contains the vertices of a polygon. So we're going to go back to this triangle, draw a circle on the grid that will go through that vertex, and that vertex. To help us do that, we're going to use the circumcenter, point Q, as the center of the circle. If we were to take a compass and set the distance from Q to any one of those vertices, and then turn the compass around in a circle, that would draw the circumscribed circle around that triangle. Let's do that. Here you see that circle drawn in brown. The center of the circle is point Q, and its radius is just enough to reach to all 3 vertices. This circumscribes, or is drawn around the polygon. And that is the reason why this point is called the circumcenter, the center of the circumscribed circle. Cal located the incenter of triangle AGC. He estimated that the coordinates of the incenter are approximately 14.4, 8.9. On the grid below, carefully draw the 3 bisectors of the angles and label the point of concurrency I to find out if our drawing supports Cal's results. So we want to find angle bisectors. To find an angle bisector, the technique would be to put a protractor on this angle to find how many degrees it is, divide by 2, and then to put the protractor back on there to draw an angle that would split it perfectly in half. You can't easily put a protractor on the computer screen, so I'm going to try to just freehand draw the angle bisector. I'm trying to make that amount of space look to be exactly the same as that amount of space. Same thing up here. I want to just kind of freehand draw the angle bisector. Okay, I want, again, that to kind of look equal in size to that right there. And the last one here, we want to split angle G right in half. How's this look to you? Does that amount of space kind of look the same as that? Something like that. Those 3 lines are the angle bisectors of the angles of the triangle. They are, in fact, concurrent. They touch each other right there. We're asked to call that point I for the incenter. Does our drawing support Cal's results? Cal got 14.4 and 8.9. And yes, that dot does look like about 14.4 and 8.9. To explore a special property of the incenter, Cal needs to calculate the distances from the incenter to each of the 3 sides. Number 7, draw a perpendicular segment from point I to segment AC and label that point L. So perpendicular segment from point I to AC. I want to draw right to AC, and when I touch AC, I want to have a nice 90-degree angle there. We're supposed to call this point L. Cal estimated the coordinates of L to be 6.1, 12.3. Find length IL. And to find a distance, you use the distance formula. So you take the difference of the x-coordinates. So the x-coordinate for point L was 6.177, and subtract the x-coordinate for point I, which was 12.4, squared, plus, and now the difference of the y-coordinates. So that's 12.353, subtract, and then the y-coordinate of point I was 8.9. Simplify this result to find the length. This turns out to be approximately 8.95 units long from point I to point L. Okay, number 8, draw a perpendicular segment from I to segment AG on the triangle and label the intersection M. So AG is right across the bottom, so to be perpendicular to it, we just want to drop straight down vertically, and that will guarantee we hit at a 90-degree angle. We're asked to call that point M. Then find the length of the green segment. So if we find its coordinates, use the distance formula, we will find that length to be about 8.95. In fact, on the screen, don't the two green segments visually look congruent in length? Number 9, draw that final perpendicular bisector and label its point of intersection B. So we want to draw from this point up to that final side of the triangle, making sure that we strike it at a perfect 90-degree angle box. If we go up at the wrong direction, there wouldn't be a 90-degree angle there. Similarly, if we angle it too far down here, that's not 90 degrees. We want to hit at a 90-degree angle box. It's going to ask us, how long is that green segment? Well, it looks the same as the other ones. So if we did out the algebra work with the distance formula, we would find it was 8.95. These distances suggest that the incenter of a triangle is equidistant to the sides of the triangle. Number 10, sketch the inscribed circle on the triangle in item 6. So previously we had drawn a circumscribed circle, a circle that went around the triangle. This time we want to draw an inscribed circle, a circle that's inside the triangle and touches it at all three sides. To help us do that, we use I as the center of the circle, and then we would set a compass so that the radius of that compass is this length here, the one you see in green. It'll look something like this. And there's the circle in green. Notice that the circle is in the triangle, so it's an inscribed circle, not a circumscribed circle, and that the center of that circle is point I, the incenter. The word incenter means the center of an inscribed circle. And finally, number 11. Refer back to the description of the nature preserve at the beginning of the activity. We were asked to locate visitor centers at the corners of the nature center. We were asked to find the power station so that it would be equidistant from those visitor centers. And we were asked to find a campground so that it would be equidistant from the sides of the triangle. And so here I've marked those. V1, V2, and V3 at the vertices are our visitor centers. Here's point P. It is the same distance from every visitor center. To find that, we had to find the point that was equidistant from the vertices of a triangle, and that was called the circumcenter. Finally, the campground, it's located an equal distance from the side, and side of the triangle. So to be able to find that campground, we had to find the incenter. of the triangle. Here are some check your understanding questions, so I'll pause the video. In this lesson, we determined the points of concurrency for the perpendicular bisectors and angle bisectors of a triangle. They were called the circumcenter and incenter. So in activity 14, you learned 4 different kinds of segments that you can draw in triangles: altitudes, medians, perpendicular bisectors, and angle bisectors. And in every case, there was a particular point that is located at the intersection of those segments.